which it will. All right. So with last time, we basically finished up with what we were really going to do with the alcohols. Now we really don't have a lot to talk about in terms of the ethers, except for how to make them and using the epoxides, which is a big deal for us. So in terms of making ethers, the most common method is called the Williamson ether. And it looks like this. I start with an alkoxide and a different or the same alkyl halide. Put them together. This is an SN2 reaction. I get the ether as my product. The alkoxide is just deprotonation from the alcohol. Usually that's going to be done with something like sodium metal. There's a couple of other ways to do it, but sodium metal is the easiest to give us an alkoxide. Then we have a straight up SN2. The problem is that we still have the limitations that the SN2 presented all along, which is that we cannot have a tertiary group on our alkyl halide. We also can't have an aromatic group or anything that doesn't do SN2 reactions where our halide is attached. So in this case, it means R prime cannot be tertiary, cannot be aromatic, cannot be alkene or alkyne, can't do it. Because we can't do substitution the same way on carbons that are not sp3 hybridized unless they came from sp3 hybrids, which is an SN1. This reaction does not work as an SN1 reaction. That is a strong nucleophile. It's also a reasonably strong base, which means if we don't get an SN2 to react, we're probably going to see an E2 instead. So, a couple of problems that go with that. One, if I want to make something like that. Well, first glance of making an ether is just to look backwards at one side is the alkoxide, the other side is the alkyl halide, but in this case, that doesn't give me two equal possibilities. If I look backwards like this, bromobenzene and the isopropyl alcohol alkoxide, what I get is absolutely nothing. That will not undergo any reaction that's any usefulness. Because my halide is not on a sp3 carbon, it's not going to react under these terms. On the other hand, if I look at it as the other alcohol, as the alkoxide, and the other group as an alkyl halide, this is a secondary alkyl halide, this is an alkoxide, this will work. So this will work very easily. So usually, well, always there are two possibilities, but usually one of them is preferable. In this case, it's not just preferable, it's one will work and one won't. The same would be true if I had a tertiary group. The same would be true if I had an alkene. The same would be true if I had an alkyne. None of those will work with the halide attached to a carbon that's not sp3 and is not accessible. This is the big one. I mean, literally, we could do 100 examples of it, but this is pretty much the way that ethers are made, with very few exceptions. There's not really any other good ways that are common that have reasonable starting materials. The only two exceptional ones are, one, is we can do what's called a solvomercuration. So if I do something like this, if I did an oxymercuration, what I would see is I would get an alcohol on the more substituted carbon because it's the better cation. That alcohol comes from water. In a lot of reactions, if we substitute an alcohol for water, we're going to see the same type of thing happening. So here's what that looks like. If I use the oxymercuration conditions, but instead I use an alcohol. So I'm just going to make it ethanol to make it simple. And then the same reductive conditions, what I'm going to see is instead of an alcohol on the more substituted carbon, I'm going to see the ether there. This reaction takes one of the hydrogens off the oxygen. With water, there were two of them, I have one left. With an alcohol, there's only one, I have none left. The carbon group is not lost. This is a difficult reaction to do. First of all, alkenes are not necessarily easy to come by once you leave simple ones behind. Two, at least on the industrial scale, handling mercury salts is probably something most companies would not want to do. Hazardous waste, expense, and things like that. So it's got some problems. The Williamson ether is much easier, which this is not. I should have erased the title on it. This is not a Williamson ether at this point. The Williamson ether is much easier, but this occasionally will help us fill in some gaps we couldn't do, because notice what happened on this one. I have a tertiary carbon attached to my ether. I had limited ability to do that from the SN2 reaction. So it gives me an option to do some things I couldn't have done with the Williamson ether. Generally speaking, ethers are unreactive. There's really only one condition where most ethers will react. So if I have something like this, I can go strong base, weak base, weak acid, and get nothing. Doesn't do anything. Really, the only time that ethers react is under strongly acidic conditions. So if I take something like a strong acid, then I might actually start to see something happen. I might see a reaction occur. But why? So let's reverse what we did before. If I treat that with HBr, what's going to happen? Logically, what's going to happen here? Okay. Protonation of the oxygen first. Good. Okay, now what? Remember, when you see strong acid used, you're usually talking about the 1 type pathways, SN1 and E1. We're not really looking at E1 here. This is going to be an SN1 reaction, which means the next thing we have to think about is a cation. So if that now protonated ether becomes a leaving group, which way does it leave? One of them will be an alcohol, one of them will be a bromide. The question is which is which. And that's defined by which of them is a reasonable cation and which is not. So you've either got a secondary cation or you've got an aromatic one. We haven't talked about aromatic rings a lot yet, so it's a bit of a loaded case. No, it doesn't. That's why I said we haven't talked about it yet. It's a bit of a loaded case, but it does not actually have resonance. The reason for that is that if we look at the aromatic ring on its side, so we're looking at this, the pi bonds orbitals are all parallel in the y-axis. My new cation orbital is here. It's orthogonal. It can't participate. So it has no resonance. It has very little in the way of hyperconjugation. Aromatic cations are very difficult, very unlikely. Not completely impossible, but pretty close. Secondary cation, on the other hand, would have hyperconjugation from all three of those hydrogens and all three of those. That's not bad. It's not great, but it's not bad. So we're going to see it happen like this, which is going to give me the aromatic alcohol and a cation on a secondary carbon. One of the things to keep in mind as we deal with cations is the possibility of rearrangement. It's not really a big deal here, but if we're generating a cation from something complicated, it could potentially rearrange if we run it through an SN1 pathway. In this case, it doesn't have anywhere to go. So what we get back at the end of this are the precursors we had when we made the ether. Even though this is going through an SN1-like pathway, we're still going to end up with the same basic preferences, albeit for different reasons. The aromatic ring can't undergo SN2 reactions. It also can't form a stable cation. So it couldn't go forward. It can't go backwards. It has to be stuck to that oxygen in both directions. This is really the only practical ether reaction that there is acid cleavage with a very strong acid. If I use something like sulfuric acid with water, I'd get two alcohols. But generally it's done with something like a halo acid so that one of the products is an alkyl halide. The reason you do that is because it's much easier to get rid of that way. It evaporates more easily. Alcohols have hydrogen bonding. They tend to have higher boiling points. So doing it this way, one of them will be selectively much easier to remove than the other by distillation or evaporation. Okay, so those are the useless alcohols, the useless ethers. Not useless. The reason that we use them for solvents so often is that they are polar. They are aprotic, meaning no OH, NH, or SH. And in terms of strong bases, strong nucleophiles, the conditions we would normally find very challenging, they're unreactive. Their problem, as I mentioned last time, is they tend to be wet. So to use them for those type of reactions, we have to dry them actively first. But in terms of their own reactivity, they don't have any. So they're very good solvents for difficult nucleophile reactions because they're not going to do anything else. The ones we use most commonly, diethyl ether, we looked at that one last time, and tetrahydrofuran. Those we use all the time. Most functioning organic labs that are research labs will have stills for both of those running 24/7, along with 2 or 3 other solvents. You'll just have this wall of stills because you need those literally every day in a working lab. So it's better just to have a permanent piece of equipment for it than to have to break it down, set it up, and do it again. So the other type of ether that we're going to deal with are these, the epoxides. That's an older term. The technical term is oxirane. But epoxides is one that most people have heard of. It's one that a lot of books will still use the terminology. The reaction is called an epoxidation. And it's called that because that's what it forms. It's a 3-membered ring with an oxygen in it. There are a couple of different ways to make this depending on what else is around. The most basic starts from an alkene. and a peroxy acid, which is a carboxylic acid with an extra oxygen between the O and the H of a regular carboxylic acid. So that tells you extra oxygen likely wants to get rid of an oxygen. The leftovers would be a carboxylic acid, likely to be stable. It is. This is a very ugly one-step mechanism. I warn you about that ahead of time because it does have a rather abnormal number of arrows involved in it, and you kind of have to watch where you place certain groups. This reaction requires a certain conformation for the peroxy acid, otherwise it doesn't work. That conformation is it basically has to wrap around on itself. And that is, we have to be looking at something like this, where essentially I've got hydrogen bonding from the acid end to the carbonyl in the middle. It's a 5-membered transition state at that point. That's what makes this really possible, is because there's going to be an electron flow in this area that's cyclic. We're going to see the electrons involved here going in a circle. We're also going to see some other strangeness here and there. The way to draw it that's the easiest is to basically just track out one of the pi bonds is going to break. That's common, to take that hydrogen as a formal covalent bond. That is going to go after the alkene. The alkene is going to come back at the same oxygen atom. That's going to require giving up the other oxygen atom, like so. That's the complete set. So there are, depending on how you draw it, I draw it with 4 arrows, which is 8 electrons. If you use the lone pair here that's hydrogen bonded and then break that, you'd have a total of 10 electrons involved in this mechanism in one step. That's abnormal. Normally we don't see more than 6, and for most reactions we don't see more than 4. So getting up 8, possibly 10 electrons involved is a little on the odd side. But it is pretty well defined experimentally. What we see, putting everything exactly in the same places, but with the new bonds, is this. So putting everything basically where it was before, the H is now attached to the carbonyl oxygen. The pi bond is gone. A new pi bond has formed, and the oxygen that was between there is the one that now makes up the epoxide. So it's a little bit on the complicated side. It's not a bad thing, but it's a little bit ugly. That's one way to make epoxides from alkenes. The other way involves using the Williamson ether, which is to say, if we take the alkene and do a halohydrin reaction on it, which is the halogen and then water, we're going to get eventually this, the halohydrin. Probably is a mixture of regioisomers. Really doesn't matter. If we then treat this with base, which will take that hydrogen, we're going to be looking at this as an intermediate. That is going to do an intramolecular Williamson ether to give us the epoxide. 2 steps, but peroxides tend to be a little difficult to handle depending on which one you're using, so this might be considered to be a little safer on a big scale. For the most part, a very small number of peroxy acids are actually used for this because there are not that many of them that are stable in high enough concentrations to use them. If you try to use them in high concentrations, a lot of peroxides become explosive. So the most common one is this, which is metachloroperbenzoic acid. Better known as its acronym, M for meta, C for chloro, P for per, B for benz, and A for acid. The reason for that is it's shelf stable as a solid. Those are the big ones. It can be stored reasonably easily, and it's not a liquid. It's actually a solid. You can actually weigh it out on a balance to use it. Instead of having to put it in solution and deal with dilutions and concentrations, this is easy to handle. It's still not 100% peroxide, because that still would be a little problematic, but the chlorine on the aromatic ring is electron withdrawing, and that chills things out a little bit. That actually makes it more stable to handle. Probably also makes it a little less reactive, but that's never been a big problem here. So it's preferable to a lot of other problems. Now, in terms of using the epoxides, they're everywhere. We looked at a couple of different things on that front earlier in the previous course. I did them out of order because they made good sense when we talked about SN1 and SN2, because you can actually directly see it here. If you have a strong nucleophile, it's going to open that ring. And it's going to give you an arrangement like that. If you don't, you can protonate it first and then come in with a weaker nucleophile. This is less commonly used, but still we have to consider it. We have to consider it because that's the type of conditions that we'll run across when we're cleaning things up. That's our extraction and our purification conditions. So we have to be really careful with pH as we're purifying this after we've made it, because we may accidentally destroy the ring we wanted. In practical terms, we also have the possibility of regiochemistry based on the substitution pattern. So if, and I think I used this on your exam last semester, if I have something like this and I use something like methoxide and acid, well, that's a strong nucleophile. I'm going to be looking at an SN2-like conditions. If, on the other hand, I say, all right, methanol and sulfuric acid, that's a weak nucleophile, and those are SN1-like conditions. What I get is two completely different products based on regiochemistry. What happens to the one on the right? Where does the alkoxide end up? Where does the methyl group end up? Less substituted. SN2 is about access. The easier one to get to is the one that gets the nucleophile, right there. So we're going to be looking at this. Well, as our intermediate, which we'll protonate afterwards during the workup. In the other case, the first step is going to be protonation. So I'm going to be looking at going from this, which I could actually draw this as already ring opened. It's not really resonance, but it's not unreasonable either, like so, because the tertiary side is going to be a much better cation. So either way I want to draw it, this probably makes more sense to what we see. I can now bring in a weak nucleophile like an SN1 reaction, and that's going to take me to here, where I now have the alkoxide, after I neutralize this protonated form of it, on the more substituted carbon instead of the less. Switch-ups like that are critical to our ability to make things, where we can switch what carbon gets which substituent. This is a big, big part of using the tools you have, is knowing how to direct where they go. There are other ways to do some of the same stuff, but the epoxide gives us openings that we didn't have anywhere else. A couple of noteworthy examples of the strong nucleophile is one, you can do it with lithium aluminum hydride. So you're basically opening it with a hydride. It will open to the less substituted side. So if I have something unsymmetrical like the one I have over there, I'm going to end up with a more substituted alcohol, and my nucleophile was a hydrogen. I'm just labeling it so we're clear where it came from. We can also do the same thing with a Grignard reagent, which allows me to do a chain elongation. Usually, this is going to be something complicated, and the epoxide will be something very simple, but what I get is a 2-carbon longer chain with an alcohol at the end of it. So it allows me to extend the functional group away from whatever R was and go from there. Because a lot of what we're going to do with epoxides is SN2 reactions. Those are both SN2 reactions. This is on the right is an SN2 reaction. Most of the useful reactions we have for epoxides are SN2 reactions. Because that's the case, we're actually going to have stereochemistry issues too.